Let's look now at the idea of instantaneous velocity. In our previous video, we looked at average velocity over short time intervals. The example we looked at was a bus whose position was given by the function 2x squared, where x was the time that the bus had been traveling, measured in seconds. The function then was f of x equals 2x squared, and we used the formula for average velocity, which was delta y over delta x, or written in terms of f, it was f evaluated at x plus delta x minus f of x divided by delta x. We let x of 0 equal 3 seconds, and then we looked at the average velocity between 3 seconds and 4 seconds, which was delta x equals 1, and we saw that the average velocity was equal to 14 meters per second. Second, we looked at a value of delta x equals 0.1, so we're finding the average velocity between 3 and 3.1 seconds, and then the average velocity, delta y over delta x, was equal to 12.2 meters per second. Averaging it over an even shorter time interval, delta x equals 0.01, we found that delta y over delta x was equal to 12.02 meters per second. Looking just at these three examples, it appears that as we average over shorter and shorter time periods, the average velocity is getting closer and closer to 12 meters per second. Let's see if that's what's really happening. Let's continue to let the position of the bus be given by 2x squared, measured in meters, where x is the time measured in seconds. And let's calculate the average velocity between time 3 seconds and any later time. So we'll let delta x equal any number, although we're generally going to think of delta x as being a small number. The average velocity will be given by what's called the difference quotient, delta y over delta x, which is f of x naught plus delta x minus f of x naught over delta x. Or in this case, since x naught is 3, this will be f of 3 plus delta x minus f of 3 over delta x. Let's substitute into the given function and simplify. F of 3 plus delta x will be 2 times 3 plus delta x squared. Then substituting 3 into the same function, I'll have 2 times 3 squared, all divided by delta x. Continuing to simplify, I'm going to take that 3 plus delta x and square it. Just as a reminder, that'll be 3 plus delta x times 3 plus delta x, which is 9 plus 6 delta x plus delta x squared. Remember that delta x represents a number altogether. It's not a number delta multiplied by another number x. Also, when multiplying these two binomials, remember that you have to FOIL it out. So substituting that back in, this will be 2 times 9 plus 6 delta x plus delta x squared minus 2 times 3 squared, which is 2 times 9, all divided by delta x. If we distribute the 2 in front, the numerator will then be 18 plus 12 times delta x plus 2 times delta x squared minus 18 all divided by delta x. Now happily, this 18 here cancels with the 18 at the end. And we have 12 delta x plus 2 times delta x squared all divided by delta x. We can factor a delta x out of the numerator, which will leave us with 12 plus 2 delta x all divided by delta x. And the factor of delta x will cancel from numerator and denominator. So the average velocity is given by 12 plus 2 times delta x, no matter what delta x equals. So for example, in the first example we did last time, we had delta x equals 1, and we got an average velocity of 14. And notice that that's exactly what we get if we substitute in a delta x equals 1 here. So to summarize, for the function 2x squared and an initial time of 3, if delta x is any number, so any time interval, then the average velocity, delta y divided by delta x, is given by the formula 12 plus 2 times delta x. So as we find the average velocity over shorter and shorter time periods, we're letting this delta x get closer and closer to 0. Well, as delta x gets closer and closer to 0, twice delta x is also getting close to 0. So we end up with an instantaneous velocity of exactly 12 meters per second. So the instantaneous velocity is equal to 12 meters per second. Now this idea of letting delta x get closer and closer to 0 is invoking an idea called limits, which we're going to be studying a little bit more in the next couple weeks, and in a little bit more depth at the end of the semester. To review though, in order to calculate instantaneous velocity, there are going to be 3 steps that we go through. First of all, we're going to find the average velocity between time x0 and x0 plus delta x. This expression for delta y divided by delta x is known as a difference quotient. So this expression here is the difference quotient. Next, we're going to simplify this expression as much as possible. That's going to involve multiplying out the numerator, factoring things out, canceling as much as you can, and eventually we hope to cancel delta x from the numerator and denominator. Once we do that, we're going to find the instantaneous velocity by letting that delta x get smaller and smaller, eventually hopefully being able to set that delta x equal to 0. This last step is going to be what we study more when we study limits.